Hi. So today we are going to go through quadratic variation of Brownian motions. So in the last video we covered what Brownian motion is, what some properties of Brownian motion is. Um, let's go over that quickly. It has martingale and Markov property, um, which basically says that um, two things about Brownian motion. First thing that it says is that um, given n processes, uh, the n plus 1th process depends on the latest process that has happened uh, about which we know. So if the nth process has happened and we know the nature of it, the process or the yeah the event at n plus 1th instance is just dependent on nth event. And the second thing it says is that it follows the martingale property, which says that expectation of wt, given that we know we have information until ws, where s is smaller than t, is equal to the value of e of ws, which is ws. Now also we also learn about the probability density function of Brownian motion, which is similar to normal distribution, and we also saw that it follows it's not Lipschitz continuous. And now we move to quadratic variation of Brownian motion. So it turns out that Brownian motion has same quadratic variation as a random walk and the scale down random walk. Here we just state this fact without any proof. That's yeah. So that basically says that quadratic variation of wt is equal to t. The natural question is how the quadratic variation is defined in general. So far we have defined the quadratic variation in two particular cases: symmetric random walk in discrete time and a rescaled random walk in continuous time. To this end, we need to consider the general partition of time interval 0 to t. Say that t0 is equal to 0 and t0 is less than t1, t1 is less than all its adjacent numbers until tn, which is greater than tn minus 1, and tn is equal to capital T, where n is a positive integer. I also denote by h the size of the largest subinterval. So basically it is the largest value between the interval that comes comes here. So between all these intervals, the largest value of differences of two values is h. I mean the largest value of differences of two intervals. We can then define a quadratic variation of any function f of which variable t by setting ff is equal ff of t is equal to a limit h tends to infinity, n tends to infinity, summation of ftj minus 1 whole square. For all the stochastic processes, the quadratic variation is computed pathwise for any given fixed outcome omega, or omega. Is this omega? I think it's omega. And hence itself is a stochastic process in general. In addition, for the sake of completeness, we recall that interpretation of almost surely. This means that the statement is true for almost all sample paths except for a set of sample paths. The set of sample paths for which the equality is wrong has probability 0. It is worth mentioning that any function which has continued derivatives has a quadratic variation equal to 0 factorial. So any function that has a continuous derivative has a quadratic variation equal to 0 factorial. Any function that has continuous derivative has a quadratic variation of 1. The non-zero or 0 factorial, which is 1. The non-zero quadratic variation of Brownian motion comes from the fact that Brownian motion is not differentiable. Finally, we note that the quadratic variation of Brownian motion is deterministic. I does not depend on particular outcome omega and is equal to its variance. So quadratic variation of Brownian motion is equal to its variance. I think that's the only fact that we need to know from reading this. Brownian motion, quadratic variation is equal to variance of the equation. Let's move on to a new topic. It's called hitting time. In this section, we define the first time the Brownian motion hits the point A. For instance, we assume that A is greater than 0. We then denote the first hitting time by tau A. It is defined by tau A equals to infinity, t greater than equal to 0, wt greater than equal to A. Next, it is natural to ask how we can compute the distribution of tau A, probability tau A less than equal to t. In this computation is based on the reflection principle. First of all, we need to write PWT greater than equal to A equals PWT greater than equal to A given tau A is less than equal to T into P probability of tau A being less than equal to T, and similarly we check for the we calculate the probability for the opposite or the complementary condition, that is that PWT greater than equal to A being tau being greater than T and probability of tau being greater than T. Then the second term in this right hand side is necessarily equal to 0, because if Brownian motion has not hit a yet by time t, it cannot be above A. Okay. Well, if they say so, I think that must be true. Basically, it's saying that if this is not true, this can never be above A. I think that's what it's saying. When tau A is less than equal to T, the process hits a point A at some time smaller than equal to T by the so-called reflection principle, which gives us this this means that knowing Brownian motion hit A before time t, the Brownian motion is likely to be above A than below A at time t. Basically it says that its outcome is still random. Consequently, we can reduce the distribution of first hitting row for any A greater than equal to 0. Again, I think this looks like a normal distribution with mean 0 and variance equals t. Which is the equation, which is the distribution of Brownian motion. From this, I think the only thing that we need to derive is or understand is that how we reach to this equation. uh, okay, so this is the result that we have obtained. It says that infinity of t greater than equal to 0 minus wt greater than equal to minus a. um, Suppose that wealth of a camera is modeled using arithmetic Brownian motion without drift. Um, this is the equation for arithmetic Brownian motion, where x naught is camera's initial capital, sigma greater than equal to 0. Sorry, greater than 0 is the volatility coefficient, and we can define the time of ruin as the hitting time. And we just got the formula of hitting time as this. In here, our A is x naught by sigma. Okay. So t greater than equal to 0, RWT is greater than equal to minus x naught by sigma, and we deduce the distribution of tau 0. It is worth mentioning that this type of computation is very commonly used in industry in practice area of credit risk. So basically calculating this probability of ruin gives us 2 1 minus phi mod x naught by sigma root t. um, okay, so it said some things about barrier options, and also said that reflection principle helps in computing that. In credit, Merton and subsequently Black-Cox developed a model for pricing equity in bonds that have a risk of default. In this model, defaulting occurs when value of an asset of the company AT, usually modeled as GBM, falls below a prescribed barrier. The case of a geometric Brownian motion is more complicated than the case of arithmetic Brownian motion, and it won't be covered in this lecture. Um, we introduced before geometric Brownian motion as limit of rescaled multi-period binomial tree model, and I explained how it was used modeling an asset price. This time we complement the study by computing the expectation of geometric Brownian motion. Let us consider an arithmetic Brownian motion with drift. So this is the drift factor, and if you look at normal arithmetic Brownian motion, it has just a constant value x naught, having this mu and this t factor. Basically, mu is the mean and t is time. So basically, this drift is created with time. That's what it means. And WT is the standard Brownian motion, and the geometric Brownian motion. Xt equals x of t is equal to e of yt. We compute xt equals e of yt as this. So geometric Brownian motion is written as E of mu t sigma w t, where z is the standard normal variable. Okay, yeah, so this was normalized, that's why the z value came in here. Basically when you normalize this is a normal distribution with a mean 0 and variance t, and this becomes root t when you normalize it. Now it has z has standard deviation of variance of 1 and mean of 0, so it's a standard normal distribution, normal random variable. Then we calculate this, and this is basically equal to this. I think this means that this will be equal to 0, 1, and then we reach here and this is 1. This is the equation, I mean the expectation of xt. I think this is straightforward. Consequently, when we look at st equals s e raised to yt, so this was xt where xt was equal to e of yt. Now we have st which is equal to s into e of yt. Then we clearly have s naught equals s, like we had x naught or s naught, x naught in the arithmetic Brownian motion. Similarly, we have an st as s0 as s. So given that we have the information s naught equals s, the price st or the expectation st, again we know that this is s is equal to s e raised to mu plus 1 by 2 sigma squared into t. We can also generalize and write for theta t with theta less than equal to t as e of st given u which is less than equal to theta and obviously greater than 0 equals s theta e raised to mu plus half sigma square plus t minus theta. So this is also an important formula that you should write down. So given st and su, u less than equal to theta, obviously greater than 0, we have the price of the stock as s theta into e raised to 1 mu t plus half sigma square t minus theta. Yeah. So that's it for this video. I'll be covering, I think, black shows in the next one, so stay tuned, and yeah, that's it. Just stay tuned and keep learning.